let's do some examples. So we'll evaluate the integral over c of x squared y ds, where we better actually describe what c is. Right now it's just a letter that hasn't been defined, where c is the upper half of the unit circle. Okay, so first time around, so we're going to take this a little slower, right? So let's just, you don't need to write a thing like this in the future, but let's just get all the pieces and match the notation to the generic story from above. F of x comma y is, in this case, the function x squared y. Now c, it's been described in words here, but we need to parameterize it. So c is parameterized in the following way. Here's the information we need. Like x, let's just call it x of t. X of t is equal to cosine of t. You could just call it x, but let's call it x of t equals cosine of t. Y of t is equal to sine of t. And upper half. So t just goes between 0 and pi. Okay, that'd be the upper half. Just to match up the notation with the generic version that we saw earlier, those will be our a and our b. Okay, we are going to, by the way, need the derivative of x with respect to t. So based on looking at cosine of t, we'll have here a negative sine of t. We'll also need dy dt. We're going to need them anyway, so let's just compute them right now. So differentiate sine of t, we'll get cosine of t. Let me just point out how it is that we're going to need them just from the previous. It's over here. You see there's a dx dt and a dy dt. So since we're going to need those anyway, let's just compute those, right? In fact, maybe it'll, sorry, since this was in an earlier part, why don't we just copy this over down here, just for reference sake. That's all. Okay. All right. So now what? Then we're basically going to apply this, or rather that it was integral over c f of x comma y ds equaled this. So here's what we're going to do. So the question we were asked, yeah. So the integral over c of, let's just call it, instead of x squared y, we'll just call it f of x comma y. Okay, f of x comma y ds. What is it? This is going to be equal to integral a to b, so 0 to pi. Okay, so 0 to pi. And you look at what we have next here. This says f of x of t comma y of t. In other words, for the first entry here, for x, we've got to plug in x of t. We need to plug in this. I mean, you get what I mean? Like, maybe we'll just work let's just work out a little more scratch work, maybe off to the side, because it's the first time around. So this f of x of t, y of t. So plugging in for the x here, we're plugging in x of t, which was this thingy here. So yeah, plugging in for this. So we got something square. Let me write the square first. Maybe that'll help. There. The square is writing that square. Now, to plug in for the x here, we should plug in x of t, which is over there. So we'll have cosine of t. Then there's a y. And for that y, we're supposed to plug in y of t, which is sine of t over there. So sine of t. Okay, so that's what we're just gonna copy this over here. So cosine of t, quantity squared, times sine of t. Let's get that in parentheses just in case. We also, then the next part is we've got this radical. We got root. And then you'll see we've got dx dt squared. So dx dt is right there, negative sine of t. So we've got negative sine of t, which we're going to have to square. Plus we have dy dt squared, so we've got cosine of t squared. And then dt. All right, let's get rid of that. So our line integral here, to be really honest, turned into a Calc 1 style integral. This is an integral that we can give to somebody in Calc 1. So integral 0 to pi, cosine squared t, sine of t, yeah, parentheses if you want. Take a look at this part. This is, okay, the negative doesn't really count because we're going to square, right? This is, inside the radical, we actually really have sine squared of t plus cosine squared of t. And then you're going to root 1. I mean, this is just times 1 dt. And literally, this integral here is one you could give to a Calc 1 student, right? Like, if you just want to work out the indefinite integral, we're not going to work any further. I mean, there's more steps, clearly, but it's a Calc 1 integral. What I'm saying is if you gave somebody the integral without the bounds of 0 pi, if you gave somebody integral of cosine squared t times sine of t dt from Calc 1, they ought to know what to do. The only thing they might be freaked out by is why does it say t instead of x? But this can totally be done, right? This is just going to be a u substitution of cosine of t. So we'll stop the problem there. Let's do another one. So let's look at, evaluate the line integral. So this will be the integral of the curve C of the function x over y ds, where C is, and this time around, look, last time we described it in words, upper half of the unit circle. This time around, I'm going to draw a picture for what C is. Okay, so we got here x-axis, y-axis. We've got this point here and a point there. Let me just draw first. Ooh, let's try that again. Okay, doot. Okay, so sorry this picture isn't perfect. I hope you get what I mean. There's this point here, 10, 3. At the top here, there's a point 5, 4. And at the bottom here, there's a point 5, 2. And let's travel this way. So this is meant to be 3 out of the 4 parts of an ellipse. Okay, so we will need to parameterize this unabashedly, right? So the parameterization, I think the most natural parameterization to use would be x of t is equal to, was it 5 cosine of t? Just because the stretch factor horizontally is by a factor of 5. Y of t is equal to sine of t. Oh, this is not quite right, huh? So it shouldn't just be 5 cosine of t. There's also a shift by 5 units, so plus 5. Oops. Y of t, yeah, the amplitude is just 1, right? Or the height from the origin. Yeah, because this is probably 5, 3. Yeah, okay. But then there's a shift, so plus 3. And then t goes from, well, 0 to 3 pi over 2. Whew. All right. Good. Now, let's set up the integral. Okay, integral of x over y, the function x over y, over the curve C, ds is, well, integral. So we need t bounds here, 0 to 3 pi over 2. Then we need, let's see, x over y, but we need the parametric versions of these. So 5 cosine of t plus 5 over sine of t plus 3. Then ds, let's underline that, is going to get replaced with root, and then we need, let's work out x prime of t. So negative 5 sine of t plus 0, and then y prime of t is cosine of t. So we need here, yeah, negative 5 sine of t squared plus cosine of t squared dt. So this entire thing is what the ds replaces. And we're just going to stop here. We'll stop evaluating the integral any further. Could it be done? It could be done. It's going to be some work, so let's not bother, right? So I think the key challenge right now is the one I want to focus on. So let's do another. Let's set up another one of these. Okay, so I'd like to evaluate the integral over c of x times sine of y ds, where capital C is the line segment from the point 312 to the point 5, 9. So you may be noticing that parameterization is a big deal, a big deal. We cannot ignore it at all. Let's just take this question and move it to the top of the next page. So we'll need a parameterization. Yeah, x of t, y of t, and then t bounds. Probably for line segment, we're just going to do 0 to 1, right? So look, we can start at 3, and then the change in x, let's see, from 3 to 5 is 2, so plus 2t. For the y coordinate, we start at 12, but then the change from 12 to 9 is a negative 3, so minus 3t. Okay, this is one way to write it. Of course, there's other ways to write it. So I hope this works. We'll need dx dt, which is going to just be 2. We need dy dt, which is going to be negative 3. So, setting up our integral over the curve c of the function x times sine of y ds is going to be the integral from 0 to 1. Those are the t-bounds. We need to then write x times sine of y. However, we got to replace the x, and we have to replace the y as well. So we're going to have 3 plus 2t, makes sense to have that in parentheses, times sine of 12 minus 3t. Okay, and then ds. We got to replace the ds with square root of 2 squared plus negative 3 squared dt. Yeah, makes sense. T there, so these are t values on the integral. This integral can actually be done. It's not well, there's some work. It's not entirely too bad. I would say, well, simplify that, right? I mean, that's just a number and bring it in front of the integral. I think the key thing, if you really wanted to go through the integral, I think maybe the key thing to say is you're probably going to have to distribute sine of 12 minus 3t to the 3 and to the 2t separately, create 2 separate integrals. One of them's, I anticipate, going to be a very easy u substitution, and the other is probably going to be like an integration by parts or something.